When you think about saving the planet and building this completely sustainable future, the mental image that usually pops up for you is probably pretty pristine.
Oh, yeah, absolutely.
Yeah.
You picture like vast fields of solar panels catching the sun, or maybe wind turbines spinning off the coast.
Right, exactly. Or maybe someone planting a tree. It has a very clean, nature-focused aesthetic to it.
Yeah, very green, very organic.
Right. But what you probably do not picture is a massive, towering factory smokestack aggressively churning out a thick plume of industrial exhaust.
No, definitely not.
Right.
I mean, for decades, that smokestack has been the ultimate symbol of environmental degradation.
Yeah, exactly.
So the visual shorthand for pollution, right? The
Yeah.
villain in the climate story that we are basically desperately trying to dismantle.
Which makes our topic today so counterintuitive. We're going to explore the possibility that reaching a 100% renewable global energy system isn't just about shutting those smokestacks down.
Right, which is what everyone assumes.
It might actually depend on plugging directly into them, like physically harvesting the carbon dioxide as it exits the pipe and utilizing that industrial exhaust to manufacture the fuel that runs our airplanes and cargo ships.
It sounds like a total contradiction. Treating carbon dioxide not as a dangerous waste product to be banished, but as an incredibly valuable, highly necessary raw material.
Yeah, it really flips the whole narrative.
It does. But this approach represents one of the most practical, economically viable pathways we have to actually stabilize the climate.
So, welcome to this deep dive. Today, we're unpacking an incredibly detailed, eye-opening academic paper.
And it's a dense one, but so important.
Definitely. And to make sure you know exactly what we're referencing, the full title of the paper is The Value of CO2 Point Source Capture for the Energy Industry System Transition.
Quite a mouthful, but it really covers all the bases.
Right. So our mission today is to break down this research and figure out if capturing CO2 directly from heavy industry is like the ultimate cost-saving shortcut to a completely renewable global energy system.
And to understand how this concept translates from, just theory to a functioning global grid, this study uses a very specific testing ground, which is Finland.
Which I have to admit struck me as a really random choice initially. Out of all the places on Earth to model a global energy transition, why focus on Finland?
I get that a lot. But Finland presents essentially the ultimate stress test for any energy transition model.
Okay, how so?
Well, first you have to consider the physical reality of the Nordic climate. The winters are intensely cold, very long, and extremely dark.
Right, I've heard they get very little daylight in the winter.
Exactly. When you have months where the sun barely rises, your solar power potential plummets exactly when your population's demand for heating is, like, skyrocketing.
Oh, wow, yeah, that is a terrible combination for renewable energy.
It really is.
Right.
But beyond just the climate, Finland possesses a massive, highly energy-intensive industrial sector. Industry accounts for an enormous 44% of Finland's final energy consumption.
44%, that is huge.
Yeah, they are dominant global players in pulp, paper, and steel manufacturing.
Okay, let's unpack this because I want to make sure I'm framing this correctly.
Sure, go ahead.
If you can engineer a 100% renewable system that keeps millions of homes warm and keeps massive steel mills running through the dead of a freezing, dark Finnish winter, you've basically proved the concept can work anywhere.
Exactly.
You're basically playing the green transition game on hard mode.
That is the exact rationale. And the core challenge Finland faces, which really mirrors the global challenge, is that even if we achieve the dream scenario where every car is an EV and the entire power grid runs on wind, hydro, and solar, we're still left with a huge problem.
Right, because we still have factories.
Yes, we are still left with what this study categorizes as unavoidable or biogenic emissions.
I want to pause on that word unavoidable. If a factory's emissions are truly unavoidable, does that mean true zero emissions is physically impossible?
That really gets to the heart of industrial chemistry. When we talk about unavoidable emissions, we are looking at facilities like pulp and paper mills, biomass power plants, waste incinerators, and crucially, cement plants.
Okay, so heavy industry.
Right. Let's look at the mechanics of making cement. The fundamental step involves a process called limestone calcination. Limestone is calcium carbonate.
Right, basic chemistry.
So to turn it into the clinker used for cement, you have to bake it at extreme temperatures to extract calcium oxide.
So you are physically breaking apart the molecule of the rock itself.
Precisely. And the chemical byproduct of breaking calcium carbonate apart is carbon dioxide.
Oh, wow.
Yeah, so even if you heat that cement kiln Using 100% pure solar electricity or green hydrogen, the chemical reaction of the limestone itself will still release massive amounts of CO2.
Because it's literally coming from the material.
Exactly. It is baked into the chemistry of the material, not the fuel used to heat it. You literally cannot manufacture cement without releasing carbon.
The carbon is coming from prehistoric rocks. I mean, I never realized that.
A lot of people don't. And the same principle applies to processing wood into paper pulp. The carbon is in the biomass itself.
Right, the trees.
Exactly. So the central thesis of this study is that instead of letting that unavoidable chemical CO2 just, vent into the atmosphere, we capture it immediately.
So we trap it before it escapes.
Right. We install a capture unit directly onto the exhaust pipe to trap the gas. This is known as point source capture, or PSC.
Okay, so we capture millions of tons of this gas. It's sitting in massive pressurized tanks next to a paper mill. How does it get from there to, like, a Boeing 747?
Well,
Because the old narrative was always about carbon sequestration, right? Pumping it deep underground into old oil wells and just hoping it stays there forever.
yeah, and sequestration is definitely part of the long-term puzzle, but this study focuses on utilization. We desperately need that carbon to manufacture the fuels of the future.
We made it.
Yes. The researchers map out something called the power-to-X economy. Power being renewable electricity, and X being whatever vital product you synthesize from it.
Okay, so what is the X in this case?
In this scenario, we need to create e-fuels, specifically synthetic molecules like e-Fischer-Tropsch liquids for aviation kerosene and e-methanol for maritime shipping.
Wait, I am struggling with the logic here. We are spending billions of euros to transition away from a fossil fuel economy to stop burning carbon. Why on earth are we intentionally manufacturing new carbon-based fuels just to burn them again?
What's fascinating here is you really have to think about the physics of transportation. Batteries have completely revolutionized passenger cars, right?
Yeah, EVs are everywhere now.
But the energy density of a lithium-ion battery is incredibly low compared to a gallon of jet fuel. Batteries are immensely heavy.
Oh, I see where you're going with this.
If you want to fly a jumbo jet from New York to London or sail a massive container ship from Shanghai to Los Angeles, current battery technology simply cannot store enough energy without the batteries themselves taking up all the weight and cargo space.
Right, the plane would just be carrying its own batteries. It wouldn't have room for people.
Exactly. For heavy long-haul transport, we are bound by physics to use high-energy density liquid fuels.
Okay, so we have to have liquid fuel. There is no electric battery alternative for a cargo ship right now. But how do we make fuel out of factory exhaust?
Through an industrial process called Fischer-Tropsch synthesis. Think of it like a molecular Lego set.
Okay, I like Legos.
You need two building blocks to make a hydrocarbon fuel, hydrogen and carbon. You get the hydrogen by using renewable electricity to split water molecules. That's green hydrogen.
Gotcha.
Then you take the carbon from that CO2 we captured at the paper mill, you put those gases into a reactor under immense heat and pressure with a catalyst, and you literally stitch them together to build synthetic crude oil. And then that synthetic crude can be refined into jet fuel.
That is incredible. But the scale of that must be mind-boggling.
It is. This study outlines a staggering projection. By 2050, the global demand for these e-fuels and e-chemicals will reach 48,200 terawatt hours.
That number is so big it's hard to even picture.
To physically build that much synthetic fuel, the global economy will require nearly 6,100 megatons of CO2 every single year.
Okay, 6,100 megatons. So we take carbon from the smokestack, build the fuel, put it in the plane flies, and burns the fuel. Doesn't that just release the carbon right back into the atmosphere?
Yes, but here is the critical distinction. It is a closed loop.
A closed loop.
We are recycling the carbon that is already above ground in the active carbon cycle. We are taking the biogenic carbon from the wood pulp, putting it in the plane, and releasing it.
Oh, I get it.
What we are not doing is drilling a hole in the earth, pumping up brand new ancient fossil fuels, and adding new net carbon into the atmosphere. The net addition is zero.
I see. It's basically a massive recycling program for industrial exhaust.
Exactly.
So if we accept the premise that we absolutely need billions of tons of CO2 to keep the global supply chain moving, the question becomes, where do we get it? Because we have two options, right? We can get it from the sky or from the smokestack.
Those are the primary avenues modeled in this study, yeah. We have direct air capture, known as DSC, which utilizes giant fans to pull CO2 straight out of the ambient atmosphere anywhere on Earth.
Right.
And we have point source capture, PSC, pulling it directly from the industrial smokestacks we've been discussing.
I was trying to visualize the difference in efficiency between these two methods. Here's where it gets really interesting.
Oh, yeah.
Yeah, getting CO2 from direct air capture is like trying to catch a specific fish in the open ocean. It's dispersed everywhere. It's like trying to vacuum a handful of dust out of the air inside a massive football stadium.
That's a great way to put it.
Because the concentration of CO2 in our atmosphere is only about 420 parts per million. You have to move and process millions of cubic feet of air just to isolate a tiny amount of carbon.
Yes, exactly.
But point source capture is like catching that fish in a barrel, or taking that vacuum nozzle and putting it directly onto the sawdust vent of a table saw. The CO2 in a smokestack is incredibly dense and concentrated.
That mechanical metaphor explains the thermodynamics perfectly. Concentrating a dispersed gas takes immense amounts of energy.
Right, because you're forcing it all together.
To determine which approach actually makes economic sense for a country's power grid, the researchers ran simulations using the LUT energy system transition model.
Which is what, exactly?
It's a highly sophisticated computational tool. It doesn't just look at yearly averages. It optimizes system costs by balancing energy supply and demand for every single hour of the year.
Every hour.
Yeah, modeling in 5-year steps all the way out to 2050.
Wait, it calculates the entire country's grid hour by hour for 3 decades.
It has to. If a wind lull hits Finland in the middle of January, the model has to figure out how to keep the grid stable, how to deploy battery storage, and how to keep these massive e-fuel synthesis plants running without interruption.
That's intense.
So the researchers ran 2 distinct scenarios through this gauntlet. Scenario 1 forced the model to rely exclusively on direct air capture for its CO2 needs.
Okay, and the other one?
Scenario 2 allowed the model to choose freely between direct air capture and point source capture.
So it's an algorithmic head-to-head competition.
Yes.
What did the model choose when given the option?
It wasn't even a contest. It was a total landslide for the smokestacks.
Really?
Yeah, by the year 2050, when allowed to use point source capture, the model elected to capture 14.6 megatons of CO2 from industrial sources like biomass plants and pulp mills.
Wow, 14.6 megatons.
In comparison, the amount it chose to pull via direct air capture was a microscopic 0.6 kilotons. The algorithm practically abandoned direct air capture entirely.
That is a staggering ratio, millions of tons versus a few hundred tons. The algorithm basically looked at the physics of vacuuming the stadium versus the table saw and said, we are going with the table saw.
Exactly, because of the cost. Capturing concentrated CO2 requires significantly less energy and much less expensive equipment.
That makes sense.
The financial impact across the entire energy system is profound. By utilizing point source capture, the annual system costs for Finland's energy transition dropped by 2.5%.
Which translates to what in actual money?
Over the timeline of the transition, that translates to roughly 3.8 billion euros saved for Finnish society.
I'm doing the mental math on the end product here. If your raw material, your CO2, is drastically cheaper to acquire, the fuel you synthesize from it has to be cheaper too.
Exactly. The study details that relying on point source capture reduces the production cost of those critical E-Fischer-Tropsch liquids and e-methanol by 8% to 13%.
Wow. Slashing 13% off the cost of synthetic aviation fuel could literally be the difference between airlines adopting green fuels in 10 years versus 50 years.
It completely changes the economics.
But as I think through the physical reality of this creates a massive geographical headache, doesn't it? Like, so what does this all mean for the physical map of our energy grid? Does it matter where these capture plants are located?
It fundamentally reshapes the map of the energy grid.
Right, because imagine you are an urban planner or a green energy developer in Finland right now.
So,
If you are relying on direct air capture because CO2 is evenly distributed in the atmosphere, you can build your billion-dollar e-fuel factory anywhere you want.
yes, you have total freedom.
You would naturally build it right next to the cheapest renewable energy source, which I assume is the massive offshore wind farms on the southwest coast.
That is exactly what the model does in the DAC-only scenario. It clusters fuel production near the cheapest electricity.
Makes perfect sense.
But the moment you introduce point source capture, you lose that geographic freedom entirely. You are physically tethered to where the industrial plants already exist. You cannot easily relocate a 50-year-old, heavily integrated pulp and paper mill just because the wind blows harder 50 miles away.
So the e-fuel factory has to go to the paper mill.
Yes. The model reveals a fascinating spatial trade-off here. E-fuel production geographically migrates away from the absolute cheapest coastal wind zones.
Where does it go?
It moves inland to regions with high point source capture potential, like center-west Finland, which is the heartland of the pulp and paper industry, or southern Finland, where there's a high density of biomass power plants.
I have to challenge the efficiency of this. Are we basically letting the location of 20th century paper mills dictate the map of our 21st century green energy grid?
It sounds wild, I know.
Isn't it incredibly inefficient to build fuel plants where renewable electricity might be more expensive just to be close to the CO2? Doesn't the cost of transmitting electricity from the coastal wind farms all the way inland wipe out whatever money you saved?
It is deeply counterintuitive, but the model proves the math works out in favor of the smokestacks.
Yeah.
The thermodynamic efficiency you gain from tapping into dense, concentrated CO2 point sources is so massive that it actually outweighs the costs of building new transmission lines or utilizing slightly more expensive, localized renewable electricity.
That is wild.
This is a massive paradigm shift for infrastructure planning. It means grid operators and urban planners can no longer just map out where the sun shines and the wind blows. They have to meticulously map industrial waste streams.
Wow.
The exhaust pipe of an aging paper mill literally becomes the anchor for a multi-billion-dollar clean energy hub.
The map of the green future is tethered to the industrial waste of the past. That is fascinating.
It really is.
But it begs a rather stark question. If point source capture is so dominant, so cheap, and so efficient, why would anyone ever bother building direct air capture? Is DA completely useless?
If we connect this to the bigger picture, it's definitely not useless. We have to view this transition as a timeline, not a single event.
Okay, walk me through the timeline.
In the short to medium term, so between now and 2050, this study clearly demonstrates that point source capture is the vital stepping stone.
Right.
It acts as the training wheels for the power-to-X economy.
Yeah.
It provides the cheap, abundant CO2 necessary to financially justify building out the massive water electrolyzers and chemical synthesis plants we need immediately.
So we use the cheap smokestack carbon to build the infrastructure today?
Yes. But there is a ceiling to this approach. We are limited by how much biomass we can sustainably harvest without destroying ecosystems.
Oh, that makes sense. We can't just cut down all the forests.
Exactly. Furthermore, industrial point sources are not evenly distributed around the globe. While Finland or Canada might have massive timber and pulp industries, other nations simply don't have enough biogenic smokestacks to synthesize the aviation fuel their economies demand.
So they will eventually have to pull it from the sky.
And beyond just manufacturing fuel, we have to face a grim climatological reality. Global temperatures have already breached 1.5 degrees Celsius above pre-industrial levels.
Right, which is scary.
Creating a closed-loop, net-zero aviation sector is fantastic, but it only stops adding to the problem. It doesn't remove the historical carbon that is already overheating the planet.
It just stops making it worse.
Exactly. In the long term, so in the post-2050 endgame, this study suggests we will likely require massive deployment of DACCS, which is direct air capture and sequestration.
Okay, so that's the burial part.
Right. We will need those giant fans to actively suck CO2 out of the atmosphere and bury it permanently into geologic formations to actually lower the atmospheric concentration and hit a safer 1.0 degrees Celsius target.
Got it. So DI is crucial. Its true value just kicks in later in the game.
Precisely.
Okay, I'm tracking the timeline, but I foresee a serious policy issue here, like a moral hazard.
Okay, what are you thinking?
If we make these industrial smokestacks incredibly valuable as CO2 gold mines, does that accidentally give heavy industry an excuse to just keep emitting?
Ah, I see what you mean.
Like, are we incentivizing a factory to keep burning dirty fuel because an airline is paying top dollar for their exhaust?
It is a critical policy trap, and the researchers navigated it very carefully. The study focuses heavily on biogenic and unavoidable process emissions.
Oh, okay. So they ruled out the dirty stuff.
Right. In these transition models, fossil fuels like coal and natural gas are aggressively phased out and replaced with electrification and green hydrogen for industrial heat.
That's a relief.
The carbon they are capturing is strictly from biomass, which is part of the natural above-ground carbon cycle, and from unavoidable chemical reactions like the limestone calcination we discussed earlier.
Right, the rocks.
Yes. It ensures we aren't just propping up unnecessary fossil fuel burning or giving a coal plant an excuse to stay open just to sell its CO2.
That distinction is vital. We are only capturing what we genuinely cannot electrify or engineer away.
Exactly.
So to pull all of these threads together, what this study proves is that industrial waste isn't just a problem. It's the raw material for the aviation and shipping fuels of tomorrow.
It is the fundamental building block.
By tapping into the unavoidable chemical emissions of paper mills and cement kilns, we can shave billions off the cost of the green transition and physically begin constructing the zero-carbon economy today using the infrastructure we already have.
And it forces a complete reimagining of our geographical infrastructure, integrating renewable power generation directly with the industrial sites we've spent a century trying to move away from.
It flips the script entirely. And I want to remind everyone that the comprehensive data and the LUT modeling behind this incredible blueprint can be found in The Value of CO2 Point Source Capture for the Energy Industry System Transition.
Highly recommend giving it a look.
But before we wrap up, there is one final, almost sci-fi concept buried in this study that I just cannot stop thinking about.
I suspect we are looking at the exact same section on synthetic biology.
Probably.
Yeah.
Because, we spent this entire time talking about synthesizing e-fuels.
Right.
But the study points out that captured CO2 can also be used for carbon-based e-materials like advanced graphene or even more mind-bending e-food.
Yes, utilizing CO2 as a primary feedstock for cellular agriculture.
I was trying to figure out how that mechanically works. The study notes a process called gas fermentation.
Right.
You take specific hydrogenotrophic bacteria, which are microbes that literally eat hydrogen for energy, and you feed them the green hydrogen and the carbon dioxide we captured from the smokestack.
Exactly.
They consume those gases and multiply, creating this nutrient-dense biomass. The study calculates that it takes roughly 120 kilotons of captured CO2 to produce 50 kilotons of edible synthetic protein powder.
It operates very much like brewing beer, but instead of feeding use with agricultural sugar, you are feeding microbes with industrial exhaust and renewable electricity.
That is just wild.
It completely decouples food production from arable land.
Think about that the next time you drive past a massive industrial plant. The very same smokestack that we have always viewed as the ultimate symbol of toxic pollution could, in the very near future, be the direct source of the protein shake you drink after the gym.
It's an amazing thought.
We are taking the jagged, messy reality of industrial emissions, and instead of just treating it like an incurable disease, we are literally engineering it into the cure. Thanks for joining us on this deep dive. We'll catch you on the next one.